Hi folks, we're going to take a look at the solution to number 11 on page 307. So here they give us this cube, so it means all the sides are equal, and they've defined these three vectors along the cube. So here we have vector A, vector B, and vector C, and they want us to write these other vectors as a combination of these vectors. Okay, so if you think, how do we combine vectors? Well, we know how to add them, subtract them, and multiply them by scalar multiples. Okay, so that's what we have access to. So let's start with noticing that all these four are just diagonals of this cube. So if I notice AG here is just one of the diagonals of the cube, and I think all the others are just, again, diagonals. Okay, so I'm going to start with AG, which I think is the easiest one because it starts where all the other three vectors that were defined starts. So essentially I have to go from here all the way to there. Okay, so I have to find a way to combine these vectors. But I want you to remember that when vectors are placed tail to tail, adding and subtracting them creates new vectors along the parallelogram formed by those vectors tail to tail. Now these parallelograms are actually squares, but that's okay. Squares are just special types of parallelograms. So I notice here that if I add vector B and vector A, I'm just going to get the vector that's the diagonal of the square that's at the base. Okay. Then what I could do is I could take this vector A plus B, and to that take vector C and move it over, which I'm allowed to do. And this here, just move vector C over there, and lo and behold, what do I get? The vector from A to G, because it's from the tail of the first to the tip of the last. Okay? So this is essentially what we're going to be doing for all of these. And it really is just about understanding that you can move these vectors wherever you like. Okay, so let's write that out. So AG, okay, was equal to A plus B, that diagonal there, so A plus B, and then to this new vector I add the vector C, which I just moved from the other side, and I get A to G. Okay, so let's do the other ones now. So here we want CE. So CE goes from here to there. Okay, and what I'm going to do is I'm going to there's different ways of approaching this, but I'm going to use the same idea as before, is that I'm going to start all my vectors from this corner here. Okay, so I know I'm going to need the vector that goes across in that direction, and then I'm going to add vector C to get to point E. Okay, so that means I need this vector here, but I notice that vector is just negative B, and I need this vector here, which is just negative A. So I have negative A plus negative B, which is just minus B, and then adding vector C. Okay, let's move on to DF. Okay, so DF, let's see, DF is from here to there. Okay, so again, let me start on this side. I'm going to have to add these two vectors. In fact, let me use a different color here. Got different markers. I'm going to have to add this vector plus that vector. So this vector here is just the vector A, and this vector here is just negative B. So A minus B, because adding the negative is just the same as subtracting. And again, I'm just going to add this vector C, which I've moved along there, to get to F. So plus C. Okay. Let's do the last one here. So printed out another cube for B because I knew this, I figured this was going to get messy here. So now we have to do BH. Okay, so let's see, BH goes from here to there. So we'll start from B. So I'm going to need this vector here, which is just B. I'm going to need this vector here, which is negative A. Okay, that's going to take me to the other corner. So this is the sum. And then again, I'm just going to add C. Okay, so negative A plus B, and then plus C. So negative A plus B plus C. Okay, and there you have it. Those are the four diagonals written in terms of those original three vectors. Okay, so main thing here is to remember that you can just put a negative sign in front to get the opposite vector, same magnitude, opposite direction, and you can move the vectors around as you need to. Okay, so let's take a look at B. And B is actually a very good problem, and one that I want you to keep in mind, because we will come to something similar later on. So we want to show that AG, or the magnitude of AG, is equal to the magnitude of BH. Okay, so that's what we're trying to do. So let's remember how we found AG. Okay, so again, use a different. So there was AG, and remember what we did. We added A plus B. Okay, this is A plus B, and then we added to that the vector C. Okay, so essentially, if I want to find the magnitude of AG, okay, well, I see that AG is just going to be the diagonal of this right angle triangle. This is going to be the hypotenuse of this right angle triangle. Okay, so in other words, AG squared is just going to be equal to A plus B squared, or the magnitude of A plus B squared, plus the magnitude of C squared. Okay, now the reason why we can do that is because, you know, we have a right angle triangle here, because these are at right angles. Okay, so all we have to do now is figure out the magnitude of A plus B. But remember, A plus B can also be considered tip to tail. Okay, and we realize that this is also a right angle triangle. So the magnitude of A plus B squared is just going to be the magnitude of A squared, the length of this side squared, plus the magnitude of B squared. Okay, so that's what A plus B squared is equal to, and then again we still have this plus magnitude of C squared. Okay, so this is an expression for the magnitude of AG in terms of A, B, and C. Okay, so let's see if we can do the same thing now for BH. Okay, so BH, remember, is that vector there. Okay, and how did we get that vector? Well, we took the vector B, we took the vector negative A, okay, and then we added those two together to get the vector negative A plus B. Okay, and then to that we added the vector C. Okay, but again, we have a right angle triangle. Okay, so the magnitude of BH is just the hypotenuse of this right angle triangle. Okay, so that means it's the magnitude of negative A, or the square of this here is the magnitude of negative A plus B squared, plus this side length here, which is just the magnitude of C squared. Okay, so now we just have to find the magnitude of negative A plus B. Okay, but again, if I put B here instead of there, I have, lo and behold, yet another right angle triangle. So that means the magnitude of this hypotenuse, the length of this hypotenuse, is the magnitude of this vector squared, okay, plus the magnitude of that vector squared, plus, of course, the one we had from earlier on, magnitude of C squared. But remember, what's the relationship between A and negative A? They have the same magnitude. So this is the same as the magnitude of A squared plus the magnitude of B squared plus the magnitude of C squared. And therefore, since the squares are equal, sorry, that should have been a square there. Missed that before. Okay, since I was using Pythagoras. So here what we found is that the magnitude of AG has to be equal to the magnitude of BH, which is what we expect when it comes to the diagonals of squares. Okay, so that's it for this one.